for joining us.
It's a pleasure.
Good to see you. I reached out for you because of you have an interesting theory, and you happen to end up on the climate denier list because of that theory. But before we get into that, can you please introduce yourself?
Yes, the name's Robert Ian Holmes. Yeah, I've been interested in climate change for probably, I don't know, 25 years, 30 years maybe. Most of my working life, I've done quite a few different jobs, but I didn't actually attend university for the first time until I was 50, and I did a degree in astronomy, and then I did a degree in mining engineering, then a master's in environmental engineering, then I did a PhD in climate science / mitigation, and was awarded that degree in the middle of 2019. Yeah, so that's a quick recap.
All right. That theory, you published a number of scientific papers of theory that contradicts the greenhouse theory. Can you please try to explain to our viewers?
Okay, it's a bit of a long story really. I was sort of in the 80s, 1980s, I sort of believed what the climate scientists were saying at the time. I didn't really take much notice. And like everyone, I was kind of a scientist at the time, was interested in astronomy all my life, believed in science, the scientific method, and I thought, well, what they were saying about carbon dioxide must be correct, that there's a greenhouse effect, the carbon dioxide we're putting into the atmosphere is adding to the greenhouse effect and so causing warming. They didn't seem to be sure exactly how much. They had a wide variety of ideas on that, somewhere between 1.5 and 4.5 degrees for what they call climate sensitivity. So what it really boils down to is climate sensitivity. What is the climate sensitivity to a doubling of carbon dioxide in the atmosphere? And the average from IPCC reports is 3 degrees centigrade. Now over the decades many papers were published which had lower climate sensitivities, and it seemed to me that over the last 15 years or so, they seem to be getting lower. Some down 1 degree, some half a degree, some even less. Yeah, it was really when I heard Piers Corbyn say that there's no such thing as a greenhouse effect and carbon dioxide doesn't cause any warming. That's really when I began to think, well, could it be true? Really need to look into this a lot more, substantially, and research it a lot more to find out exactly. I looked through the IPCC reports, and what they identify is just one climate cycle, the Schwab. That's the only one, the 11-year solar cycle, which doesn't really do much, goes up and down every 11 years, about 0.1 degree difference from top to bottom in global temperature, so it didn't really make much difference. But when I looked through the literature, I discovered that there were at least 16 climate cycles, so the Schwab is just one of 16 climate cycles affecting our climate. Now the IPCC only recognised and only mentioned the one, as I said, so it seems to me that there definitely was something very wrong there, that they weren't recognising climate cycles which definitely affect our climate. For example, the 61-year Yoshimura cycle, which peaked in 1880, again in 1940, and again in 2002. and they seem to ignore that. There was a warming from 1910 to 1940 and again from 1975 to 2000. And the first warming, 1910 to 1940, they attributed that to natural causes. And the second warming, which was almost identical, from 1975 to 2000, they attributed that to a forcing from carbon dioxide, our carbon dioxide emissions, which really took off after 1950, really post-World War II. They couldn't attribute the 1910 to 1940 warming to CO2 emissions because our emissions were very low at that time. Then I started looking to other things such as the ideal gas law and its relevance to planetary temperatures, and published a paper in, I think the first one was in December 2018, on the molar mass version of the ideal gas law, and that seemed to suggest that planetary temperatures are not really determined by greenhouse gases, but by something which is called in mining, I'm a mining engineer, autocompression. So when there's a thick atmosphere, so over 0.1 bar, autocompression, that is gravity causes autocompression of the atmosphere, forces the atmosphere down to the surface, and whenever you've got a pressure of over, like I said, 0.1 bar, 10 kilopascals if you like, you automatically get convection, and that is the primary method of heat transfer in the troposphere, is convection. But in the upper atmosphere, in the mesosphere and stratosphere, yes, radiative transfer of heat is the primary method of heat transfer, but not in the troposphere. When they're talking about greenhouse effect, they're talking about radiation, they're talking about the properties of greenhouse gases.
So what you're saying is that the climate is depending on the autocompression of the gravity of the atmosphere, and then the heat is distributed by convection. Yeah.
There's something in the atmosphere called the lapse rate. What the lapse rate comes from? It comes from the potential energy of the atmosphere higher up. When it's convected down to the lower atmosphere, that converts some of that potential energy in the gas, converts to kinetic energy. And what temperature is temperature is just a measure of the average kinetic energy in a gas. So that's why you've got a thermal gradient through the troposphere, which leads to a thermal enhancement at the surface. There is probably no effect from greenhouse gases, no anomalous effect, but there is definitely in thick atmospheres like Earth, Venus and Titan, there's a thermal gradient through the atmosphere, through the troposphere I should say, from the tropopause downwards to the surface, which leads to a surface thermal enhancement. Now because the convection is continuous, the heating is continuous. And as I said, the temperature is a measure of the average kinetic energy in the gas, and the kinetic energy in the gas in the lower atmosphere is increased compared to higher up near the tropopause. So it's that convection. At any one time 50% of the troposphere is rising and 50% of the troposphere is falling. And so 50% of it is that's descending is warming, and the 50% that's rising is cooling. So what you get higher up in the atmosphere is a temperature of about 255 Kelvin, which is predicted, that's the Earth's average temperature predicted by black body law. But down on the surface we know that it's actually 288 Kelvin. So there's 33 Kelvin higher that you've got to explain somehow. And in the 1980s, they just simply assumed that it was caused by something called the greenhouse effect. This goes back to Arrhenius in the 1800s, who put forward this idea of the greenhouse effect. But before him, before Svante Arrhenius, there was James Maxwell. He proposed the ideal gas law, and thermodynamics had a lot to do with thermodynamics. So really the cause of planetary surface temperatures in thick atmospheres is thermodynamics, and not due to radiative effects or warming from greenhouse gases.
So the change that we see, like in yearly changes in temperature, like when we have the warm period and the cold period, and like if we go a little bit past history, is that due to the change in the atmosphere's like density and molar mass or pressure? What caused the change?
Okay, what I did in my first paper was I converted the ideal gas law into the molar mass version of the ideal gas law, which is basically this simple formula here. So it's temperature equals pressure divided by the gas constant times the density of the gas divided by the molar mass of the gas. So these are averages. So, but also they can be specific. So you can get the temperature, let's say, of the average over the whole Earth by the average pressure, 101.3 kilopascals over the whole surface of the Earth. R is the gas constant, so that stays the same, so 8.314. And the density, about 1.2 kilograms per cubic metre, is the air density at the surface, and the molar mass, which is around about 28 for Earth. So when you calculate that out over the average on the surface of the Earth, you get 288 Kelvin. That's the temperature. And you can do the same for a specific point in the Earth's troposphere anyway, really. So let's take the South Pole. You can use this to calculate the temperature, the average temperature at the South Pole, which is it comes out as minus 49 centigrade. But the average over the whole Earth is plus 15 centigrade, which is 288 Kelvin. Right? So it's probably better to talk in Kelvin. What causes the very low temperature at the South Pole is this mainly. It's the low pressure. It's only about 68 kilopascals at the South Pole because it's so high. It's really the height above sea level because of the low pressure, and the low pressure is what mainly gives you the low temperature at the South Pole. So anyway, this formula can also be used on any planet. If you have a look at my papers, you'll see that Jupiter, Saturn, Mars, Venus, any planet basically with an atmosphere, Earth, Titan, or Moon with a thick atmosphere. So basically temperature, you can say that temperature, yeah, you can say that temperature comes from three gas parameters, so pressure, density and molar mass, from those three. So if you add a gas to the atmosphere, let's say carbon dioxide, it's really how much gas you add, not really which gas it is. It can be carbon dioxide, it can be oxygen, it can be water vapor, it can be nitrogen, whatever gas you add. It's only going to change the temperature in relation to its how much it changes the partial pressure, the partial density and the molar mass. So in other words, if you add a small amount of gas, relatively speaking, to the atmosphere, it's not going to make any difference to temperature, no measurable difference. So by changing, if we manage to change CO2 from 0.04% to 0.08%, it's not going to make any measurable difference to the temperature, to the planetary temperature.
Venus, the planet Venus is often used as an example of the greenhouse gas going crazy. So actually, it's not really the principle on Earth about that theory is the same on Venus.
Right.
It had nothing to do with the greenhouse.
Right. Well, they point at Venus because they point at Venus because they think that there's a greenhouse effect on Venus. But there's no greenhouse effect on Venus, and there's no greenhouse effect, I would say, greenhouse gas effect on Earth either. So the temperature on Venus has the same cause as the temperature on Earth, which is because of the mass of the atmosphere, convection, autocompression leading to convection, and the density of the gas and the pressure. So you can see temperature really as a sort of a battle between pressure and density in thick atmospheres. The lapse rate on Venus is quite similar to the lapse rate on Earth. It's about 7.7 centigrade per kilometre. On Earth it's 6.5 centigrade per kilometre. Now, in my latest paper, I compared the atmospheres of Titan, Venus and Earth at 1 atmosphere of pressure. So you can find somewhere in those three atmospheres where there's 1 atmosphere of pressure, or 1 bar, if you like. On Earth, it's at the surface, of course. On Venus, it's about 49 kilometers above the surface. And the temperature there, 49 kilometers above the surface, has been measured by various landers, various spacecraft going through the atmosphere, as being 340 Kelvin. Now, 340 Kelvin exactly relates to Earth's 288 Kelvin at 1 bar through the insulation. So if you look at the relative insulation between top of atmosphere insulation between Earth and Venus, the relative insulation difference is 1.91. So Venus has 1.91 times the insulation, top of atmosphere insulation that Earth has. And the quaternary root of that will give you the temperature on Earth. So I'll just quickly draw another formula which will explain that probably better. This formula here. Now the quadruple root comes from black body law, so in other words the temperature on Venus equals a quadruple root of 1.91, which is the insulation difference, how much solar energy Venus receives more than Earth, 1.91 times more. If you multiply that by the temperature on Earth, the average temperature on Earth, which is 288 Kelvin, if you work that out, you'll find it comes to 339 Kelvin. And 339 is the temperature on Venus at 1 bar in the atmosphere, in the Venusian atmosphere. So in other words, at a height of 49 kilometers. So the two are exactly related through solar insulation and pressure alone. So at the same pressure on Earth and Venus, the temperatures are exactly the same, only depending on solar energy, insulation, nothing else. So the greenhouse gas differences between Venus and Earth, and even the albedo differences between Venus and Earth, have made no difference to the temperature. Only the insulation, the solar energy coming from the sun, has made a difference to the temperature. Venus has 96.5% of greenhouse gases. Earth has 2.5% greenhouse gases in the atmosphere, in the troposphere. So there's a massive difference between Earth and Venus in terms of greenhouse gases. And Titan has 2.7% greenhouse gases. The albedos of Venus and Earth are again very different. Earth 30% albedo, Venus 70%. So even though the greenhouse gas contents of the atmospheres and the albedos are very different, as you see in my last paper, my 2019 paper, on these three planetary bodies, the temperature is related exactly through insulation at the same pressure in the atmosphere. It's the same for Titan. You can calculate the Earth's temperature from Titan or from Venus. Just measure the temperature in Titan or Venus at 1 atmosphere at 101.3 kilopascals, and when you factor in solar insolation, the difference, using that formula you'll find the Earth's temperature. So you don't need to discover what's in the Earth's atmosphere. You don't even need to go to the Earth's atmosphere. You don't need to check what gases are there. You know from that, from a measurement on Venus or from Titan, whichever, you can calculate the Earth's surface temperature from those planetary bodies. So all you need is to find that out is pressure and solar insolation.
So that means that if we, let's say we found an undiscovered planet in our solar system, we are able to calculate the average temperature on that planet at 1 bar. We have like distance from the sun and composition of the atmosphere.
Yes, basically, as long as there's no massive internal cause of heat from that planet, then all we need is a thick atmosphere on that planet, and to know the difference in distance between Earth or Venus from the Sun and that planet from the Sun, the relative difference, and you can calculate the temperature in that planetary atmosphere at 1 bar. So that's regardless of what the atmosphere is made of. So in other words, it doesn't matter how much greenhouse gas is in the atmosphere. This tells you that there's no greenhouse effect, no greenhouse gas effect. There's no such thing as a separate class of gases called greenhouse gases which can cause unusual, or I would call it anomalous, warming.
But how about water vapor? Does it any changes in the atmosphere?
Pardon?
That always said that is the most important greenhouse gas.
Oh, water vapor.
Water vapor. Yeah.
Yeah. Well, water vapor. Water vapor will, because there's quite a lot of water vapor compared to carbon dioxide. It will affect temperature through the molar mass. Because the molar mass of water vapor is 18, whereas the average for the atmosphere on Earth is 28. So it's going to lower the molar mass. The more water vapor you add to our atmosphere, the more you're going to lower the average molar mass in the atmosphere, because water vapor can be 1 or 2% in the atmosphere, whereas carbon dioxide is much lower. It's measured in hundredths of 1%. So it doesn't affect temperature as much through molar mass. So if you add a lot of water vapor to the atmosphere, it should actually lower the temperature of the atmosphere, because it will lower the molar mass, which tends to, in the formula I showed you first, that tends to lower the temperature. But but when you're talking about water vapor, quite often you're talking about clouds when you're talking about water vapor. So if there's a lot of clouds can reflect solar energy and so cool the Earth. So that's also an effect, a very strong effect of clouds.
So the whole temperature change in the past history, like the Roman period and Middle Age period and all the cold dark ages, is due to change in climate cycles.
Yeah, this is climate cycles. The main climate cycle you're talking about there is the bond, which is a 1,000-year cycle. It roughly, you could say, peaked in the Minoan period and again in the Roman period. then again in the medieval warming period, and then again now in the current warming period. So this is a 1,000 year climate cycle. Is rising at the moment, so it's underpinning everything. So I don't think we'll get a large drop off in temperature in the next 50 years that solar people are talking about might happen. I don't think that's going to happen because the climate is underpinned by these longer term climate cycles. There's also Gleisberg, which is an 88-year cycle, and the Yoshimura, which is a 60-year cycle. Now, the Yoshimura rose from 1975 to the present, and we're sort of on a high with the Yoshimura. There's also several other climate cycles that are sort of peaking at the moment.
So you don't see any cold period, or maybe just a flat trend in the temperature?
Looking at the climate cycles, I don't think we're going to see warming in this century, in the 21st century. It might go a little bit cooler towards 2050, 60, and then probably rise again towards the end of the century. I don't think it's going to be a strong rise or fall in either direction this century, because of the way that the climate cycles are interacting.
This theory you come up with, how did the science community receive it? What kind of feedback did?
Yeah, I've had some good support. I mean, on my YouTube channel, I've had about 10 million views over the years. I've been on there about 8-9 years. And I've had some good, some bad. I've had a lot of bad reactions especially from climate activists. A lot of threats of violence and so on. I had a mob planning to attack me at one time. So I had to take legal action in that case, but as soon as they go before the judge, they seem to turn to water, these people. Yeah, but I've had some of them say that, you're worse than Anders Breivik, It's not good out there, especially on Twitter and on YouTube. It is quite bad to have a different opinion on science, yes, on climate. There's quite
did it surprise you that you get this kind of reaction?
It did a little bit, yes. I thought that people would discuss things. Science is something you should check and recheck, and every idea, every hypothesis that's put forward has to be, checked by other people. And there shouldn't really be this kind of politics involved in it. It's a pity that it's happened, but yeah, when I published my papers, my 3 climate papers, I was lecturing at the university at the time, and they basically let me go. So last year I was basically fired from my job. But I'm not alone. There's quite a few others, even just in here in Australia. There's quite a few others. Professor Bob Carter, Professor Murray Salby, Professor Stuart Franks. There's quite a few more as well that I can think of that have been fired. Papers they publish which go against the grain, sort of thing. I suppose it matters more to the younger people who, if you're young, you've got a mortgage, you've got a family to support, then you'd probably toe the line as far as climate science goes. But if you're a bit older like me, you don't care. You just go with the flow, and yeah, that's things that happen.
Yeah. This political influence by the science has been influenced by politics for quite some decades. When did you see this coming? When did you see this turn, like from real, as you call it, real science, until like
Yeah,
political science? When did this happen?
yeah. I think really it was after ClimateGate, wasn't it, when the emails came out and we found out how really dodgy the science is, and how they were suppressing any alternative papers that they didn't like. There's only a very small number of scientists that are involved in this. There's about only 30 or 40, really, when you think about it. It's not that many. Those that are working on attribution at the IPCC, there's only a handful of them. And they seem to be, dictating world energy policy at the moment, which is a bit frightening, really. I mean, there's windmills and solar panels going up everywhere, costing a lot of money, very, very inefficient. Actually, quite bad for the environment because a lot of toxic metals have to be mined to make these windmills and solar panels. So it's not that environmentally friendly, especially if they're cutting down whole forests so that they can erect wind farms, such as they are in Scotland, for example. Yeah, I think that when you look at the West are having to cut their emissions because of the Paris Climate Agreement, but the so-called developing countries don't have to cut their emissions, and their emissions are actually larger than the West at the moment. They've grown larger. By far the biggest emitter of carbon dioxide is China. More than double the next biggest emitter, which is the United States. The United States, even though it hasn't been in the Paris Climate Agreement, its emissions have fallen quite substantially by about 1 billion tonnes per year. So even though total global emissions of carbon dioxide, anthropogenic human, is about 38 billion tonnes per year, natural emissions of carbon dioxide are about 770 billion tonnes per year. So our human emissions are only about 5% of all carbon dioxide emissions. And about half of that is taken up by the oceans and by plant life because of the excess carbon dioxide that there is in the atmosphere, excess over what there has been for the last few decades. So although when you look back on the historical record over millions of years, the carbon dioxide level now is actually very low historically compared to the past. So it's almost the lowest it's ever been virtually in the Earth's history. I don't think it's something we need to worry about. The carbon dioxide level is basically an effect of temperature. So when the temperature goes up and down, carbon dioxide goes up and down afterwards. So it's not that carbon dioxide is causing the temperature to go up and down, it's the reverse. It's that the temperature causes carbon dioxide levels to go up and down. And it's basically always been like that throughout the proxy records that we look at.
But let's say we find all the fossil fuels we can find and burn it all. Like, would we be, like, as a human, would we be able to release enough carbon dioxide to change the molar mass and density enough to affect the temperature? Like, if we use your theory about the Earth's compression, would we be able to do that?
No. It will not make a measurable change to planetary temperatures.
So no matter what we do, we burn it all and get crazy like China, then it doesn't have any effect, even like we reach like 800 parts per million.
800 parts per million, no, it wouldn't make any difference. There'd be no measurable difference to global temperatures. Of course, apart from CO2, we're talking about CO2 now. But with CO2 might come pollution. If you're burning fossil fuels, that is something we need to seriously, cut down as much as possible. In particular, the NOxes and SOxes that they talk about that come out of fossil fuel power stations. I mean, China is globally about 1,200 large coal-fired power stations are under construction right now. About 1,200 to 1,500 are either being built or in the late planning stages. So that is going to raise CO2 emissions. But if you have the correct controls on the power stations, like we have in the West largely, then you do control the dangerous pollutants such as the NOxes and SOxes and the particles that you have to control. I'm not saying there's no anthropogenic effects on climate whatsoever, but there isn't through carbon dioxide or methane or other so-called greenhouse gases. But there could be some anthropogenic effect on the climate through pollution, real pollution, that is black carbon, for example. If there's a lot of black carbon coming out of China and India, it's going to settle on snow, for example Greenland. It's going to settle on the Arctic, and that's going to cause some melting. So that, but although it'll only be temporary, but that is something that we really need to control more than carbon dioxide itself.
But I guess we have the technology to be able to remove all the particles and pollution. But I guess in the poor countries, developed countries, they maybe not want or have the funds to implement that kind of technology. So you have any more plans for like future release, like scientific papers or any more papers coming out from you?
No, I don't think so. I've no plan at the moment for another paper. I'm in the late stages of writing a book which might come out. So if I can stop being so lazy and get it finished. It's about 95% finished. So I've just got a few weeks of work to do and then it'll be finished. But as far as papers, no, I've no plans for another paper at the moment.
Dr. Robert, thank you very much for talking to us. I appreciate it. Where can people find your work? Where can people follow you?
Oh, they can have a look at my videos on my YouTube, which is 1000 Froley, PhD, or you can follow me on Twitter. At the moment, I'm still there. I've been trying to get on Parler, but that's been shut down, unfortunately. So they're trying to stop any form of free speech by anyone, basically on the right at the moment. Which is also very disappointing, but I'm sure Parler will get going sooner or later, and perhaps some other competition for Twitter.
And we will link the description below. And thank you very much for doing this.
No worries, thanks Ricky.
Thank you, bye.
Okay.
Just hang on for a little bit until it's finalized.
Yeah, no worries, yeah.
It will show in the top corner when it's done.
Oh yeah, no worries, thanks for that.
So are you still are you in lockdown in Australia? Like COVID?
No, things are pretty well back to normal now here. We're just doing our normal thing that we always did before. The only difference is we have to wear the mask when we go to the supermarket. That's about the only thing. There's no cases really in Australia.
Oh, same here.
Yeah, there's no one in intensive care in the whole country. Yeah. There are some advantages of being an island, I think. Yeah, I know. Yeah, it's the winter over there in Europe, and that's when the viruses seem to expand very rapidly. It's the same in the US, but we got summer here, so the virus is sort of taking a back seat for the time being, anyway. Yeah, we're pretty lucky, really.
Yeah, and it's been quite cold this year. Like the winter, we have like the coldest winter like in 5 years. So
Yeah, and it was predicted by the climate alarmist like 20 years ago that the kids will never see snow again in Europe. So
yeah,
it's all down
but
to a mistake
every day.
it's all down to a mistake with carbon dioxide. They've got models that are driven by carbon dioxide. Yeah, it's very, very wrong.